We have a horizontal long straight wire that carries a current I and a vertical metal bar that is moving to the right at constant speed v. The top point of the bar, point A, is at a distance d from the wire. The length of the bar is capital L. Let's calculate the induced EMF in the bar. Here's the magnetic field created by the straight wire. By the right-hand rule, anywhere below the wire, the magnetic field is pointing into the page. Align your thumb in the direction of the current, which is to the right, and that's your right thumb. Your fingers are curling into the page below your thumb, so that's the direction of the magnetic field. The magnitude of the magnetic field is equal to mu 0 I divided by 2 pi r. I is the current in the wire, and r is the distance from the wire. So the magnetic field is inversely proportional to r. As you move away from the wire, the magnetic field decreases. Now, how to calculate the induced EMF in the bar? The magnetic field is into the page, the bar's orientation is vertical, and the velocity is horizontal. So all these orientations are perpendicular to one another. In a case like this, if the magnetic field had been constant, then the EMF would simply be equal to V times B times L, where V is the speed of the bar, B is the magnetic field magnitude, and L is the length of the bar. But because the magnetic field is not constant and along the bar B is changing, since the bar is perpendicular to the wire and B is changing with the distance from the wire, we cannot use this simple formula. So instead we are going to use an integral formula. Imagine dividing the metal bar into small pieces of length dr. Now on this small piece, the magnetic field is more or less uniform, and the EMF induced along the small piece is going to be equal to V times B times dr. And the total EMF along the entire bar is going to be equal to the EMF coming from each of these small pieces. Here I have set up my integral formula. The total EMF is the integral of the infinitesimal EMF coming from each unit element dr. And that infinitesimal EMF is equal to V times B as a function of r times dr. B as a function of r means the value of B at the location of dr. So let's substitute the formula for B as a function of r and take this integral. Here I have substituted the formula for the magnetic field, and I also set the integral bounds. R runs from D to D plus capital L. That goes from point A to B. And in the next step, I factored out all the constants. We're taking the integral of 1 over r. The integral of 1 over r is the natural logarithm. Here's the result of our integral evaluated from D to D plus L. Note that this is the magnitude of the EMF, so this is a positive expression. The next question is, which end of the bar is at higher potential? Is it point A or B? Let's think about the direction of the magnetic force acting on a positively charged particle. Now, magnetic force is charge times V cross B. For a positively charged particle, the direction of the magnetic force is in the direction of V cross B. Align your right hand in the direction of V, which is pointing to the right, and then curl your fingers in the direction of B into the page. Your thumb is pointing up. So a positively charged particle will experience a force upward, whereas a negatively charged particle, like an electron, experiences a force pointing downward towards point B. So the electrons will move towards point B. There will be a negative charge accumulated at point B, and there will be a deficit of negative charge at point A, so point A will be positively charged. Therefore, point A will be at higher potential compared to point B. If we replace the bar with a rectangular loop like in the picture, what will be the induced current in the loop? Now, from Faraday's law, we can actually see that as we pull the loop to the right, the flux through the loop doesn't change because the distance between the wire and the loop remains the same as the loop is moving to the right. So if there's no change in the flux, then there's no induced EMF, and therefore there's no induced current. Can we get to the same result using the motional EMF at each segment? The answer is yes. Let's start with segment 1. So in segment 1, there's a potential increase as you move from point B to point A. There's an induced EMF between these 2 points, and point A is at a higher potential. As you move along segment 2, there is no change in potential. There's no induced EMF along segment 2 because it's horizontal. And then you get to segment 3. Let me call this point C and then this one D. As you go from C to D, then again there's an induced EMF, but this time the potential is decreasing by the same magnitude as in segment 1 because of symmetry. And again in segment 4 there is no induced EMF. So the induced EMF in segment 1 cancels the induced EMF in segment 3. So overall there is no induced EMF in this loop as the loop is moving to the right. If there's no induced EMF, there's no induced current in the loop.